third is the satellite remote sensing. The third is the spaceborne. Okay, here spaceborne, such as a rocket and the satellite. Okay, so and the manned spacecraft. So on the satellite is, yeah, we use this most popular satellite spaceborne. The remote sensing platforms. Okay, three types. And you see, this is an in situ measurement. This machine is called the ASD field spectrometer. You see, this is the guy. Yeah, you use this here, a computer, and here is the detector. Detector. If you detect this say vegetation, you should above 1 meter or 1 meter to 1.5 meter range. Yes, above it, then the detector, and you can see from the computer, yeah, the vegetation, the wavelengths, it change. Yeah, how the wavelengths, yeah, vegetation or the different vegetation. Yes, this the curve is different. Okay, the vegetation and the soil, yeah, it's different. Okay, the curve, yes, how it's changed to the different lambda, yes, different band, yeah, how it's changed. And this is the in situ measurement. In situ measurement. Okay, it's now it's this is you see can on the neck and now it's not on the neck, just a very small one, just like our microphone, smartphone, and a very small one now. This is the old. You can see it. Yes, very clearly. And this is big and very heavy. Heavy one. This is in situ. In situ, and you see this is area platform area in the or the orbital platforms. And this is you see this side. This is aerial platform, and here is remote sensing instrument. And when it's see on the platform, see the ground object or the target from the remote. And here, this area, we say the field of view, or the or called instantaneous field of view. Simply say IFOV here. IFOV, yeah. So this area we call the IFOV, instantaneous field of view. And you see this is IFOV. If the you see the IFOV, yes, the diameter, yes, this is the diameter, and this is the platform, how the height, yes, the altitude above the ground level. This is the height, and this is the IFOV, and this is the angle of called beta. Beta IFOV. Okay, so some parameter about this to see from the platform to the target. Yeah. And this is the collection of the remote sensing data in digital format. Yeah, digital format. Then we use the collect, Then we by the data processing use the computer and can view digital information extraction use the any software. Yeah, this two processes should use software software. Then we can distribution and use for of the information. Yes, and we can um, obtain this information. Yes, and also can to uh, to get a map or the semantic map. Semantic. Yes, this is all the process, and we will by this course we will learn how to do these 4 steps. And this is for the remote sensing. For the example of for the remote sensing systems to be used the collect the mild spectral and high spectral imagery, and this 3 is for the mild spectral side, is for the TM ETM Landsat. It's used the scanning mirror, then obtain the multi-spectral bands. Use a discrete detector. And say for example, the sport it's use linear array push loop, So you see this is detector. So it's different for the sport and TM ETM. It's use scanner, and it's sport use linear array push loop. It's different. And for the camera and the film, this is just the image scale photograph by the lens, and yeah, this is very simple. It's just a photograph, and this is the scanner or the push loop use. Yeah, this is sensing images, different bands can get. This is only one in this analog frame camera. Okay, and for the for the hyperspectral data, so this 2 is for the hyper. Say AVIRS and the AIS. This it's also different. You see, for the AVIRS, it's use the linear array with whisk brain. The mirror is rotating. This is a scanning mirror for the team. This is a rotating mirror, and you can obtain n bands. This is only 4 bands. Say discrete detector, then n bands rotating. So several bands, a lot of bands, more than 100. Yes, bands use linear whisk broom. And for the AIS, yes, it's use the hyperspectral area array. You see here is different bands, and here is dispersing element, dispersing different detectors here. Okay, so maybe this is more advanced. You see here. AIS, and this is for the digital frame camera area arrays. Okay, so this is only use my camera. Okay, analog frame. This is use a digital frame camera area arrays. Also can record different bands. Okay, so but use the detectors, different detectors. Maybe here say the detectors. You can get the four bands. Yes, this lens and the filtration. Then you get the information from the object. So yeah, different um, methods or systems used to collect the image. So this is just for the introduction. You just have just for the introduction. Okay, and also photograph also can be get from the vertical and the oblique. So if you the camera orientation is the orientation of the camera related to the ground um, to, during the acquisition, it can according to the orientation can be divided vertical and oblique. A vertical photograph means the camera's optical axis equals to um, uh, plus and minus 3 degrees. 3 degrees, only 3 degrees, very narrow. Means yes, vertical to Earth. And larger or lower than 3 degrees. Larger than 3 degrees, 3 degrees maybe called or will be called oblique. Oblique. This is vertical. Yeah. Over the very narrow 3 degrees only. Narrow the 3 degrees. Yeah. And together, plus together 6 degrees. Okay, so this is AGL altitude, and this is some parameter PP. This is field of view picture. And sometimes if we want to know say the building, the height of the building, or the height of the trees, if you to see it from the vertical, you cannot get this information. So if you use the oblique view, you can see it's can compare its difference, the height of the. You see, this is a low oblique photograph of a bridge on, yeah, it's a bridge. You can see from here, you can see the bridge is this way, and you also can see it's the shadow. Yeah, maybe the sun is from here, on the left, on the left, on left, and you see this the shadow, and here the shadow, the water, water also. You can see it's the height of this um, building on this bridge, bridge. So so it's very useful. Use the oblique view, oblique, because from this we can get the attractive height, which are very useful for the site, for the urban site. Use intelligent um, urban. Yeah, you should know the different area, the height of the building, the height of the, yeah, mostly for the building. Yeah. Um, and this is a low oblique. And here you see, you cannot see the horizon. So just the low oblique. Now, if you see the high oblique, yeah, so this is the high oblique. High oblique, then the horizon is shown in the photograph. Then you can see this is the high oblique photograph of the ground. Yeah, in Washington. Yeah, you can see sunset or sunrise. You can see the high oblique. Yeah, also is the shadow. Yeah, the bridge is shadow, and the water, and it's yeah, the mountain. Mountain. Yeah. Now also this is a photograph, and also with remote sensing also can be record the image or can record with the vertical and the oblique. Yes, it depends what you want to do. Yeah, your aims, your aims. You can get the oblique. Okay. Um, and for the image, we sometimes we use different band, and also there is a panchromatic band. Panchromatic band means it's the wavelength is wider, maybe covered um, two or three bands, but its spatial resolution is high. For Landsat, you see, for Landsat TM, this is near infrared range band. Um, its resolution, spatial resolution is 3 meter, 30 meter, 30 meter, plus multiply 30 meter. But for panchromatic band, its spatial resolution is 15 meter, 15 meter. It's so we can see the same area. This is the infrared band. This is panchromatic band. Its spatial resolution is different, 30 meter and 15 meter. So you can see here is more detail. You see, this is the water, this is the land, maybe wetland, and this is vegetation, trees. You can see this is more um, more detail in this water. They compared with this one because this spatial resolution is more higher. And this is bridge. Maybe land, and this is bridge. This is bridge. So, um, but for infrared, and because it's mainly used to detect the vegetation, so maybe you can see the vegetation is the color of the vegetation is more high. So here in this image, um, the color is whiter than that one. This is dark gray. This is white. Uh, because near infrared band is in this band the trees and the vegetations have a higher digital number. So yeah, you can see it's different. It's okay, it's different. This is the white and black one, and this is for the color. This is normal color, and this is the fourth color. Fourth color means let the vegetation um, to be uh, to be the red. Red, red is the vegetation, and this is the green is the vegetation. So then we how to display in normal color or how to display in fourth color or we will exercise we will know and to do it in the exercise next time. So just here today we just give you some introduction. Okay, introduction. Yeah. Okay. So this is a normal color. The all vegetation, the color of the all vegetation is green. And for the fourth color, all the vegetation, yes, vegetation is red. Color red. You see, this is maybe the yeah the bay. You see, the bridge. The both of these sides have some trees. The red and um, uh, Next, we will introduce some multispectral and hyperspectral remote sensing systems. For example, multispectral, we use the a lot of spectral, multispectral images, such as Landsat series. All this is Landsat. And the GEOS we call for the weather forecasting, AVHR, and yes, and this is for the moderate spatial resolution or the coarse resolution, and this is using linear arrays for the high spatial resolution, such as spot, iconus, yeah, iconus, iconus, yeah, this is using linear arrays, and this is used for the moderate or coarse spatial use discrete detectors and the scanning mean. And for the hyperspectral, hyperspectral imager, we use the linear and area arrays detect. Okay, so we give some example, yes, step by step. And this is a Landsat series from the UC 1972. Oh yeah, MSS Landsat 1 called MSS. Yeah, MSS 1, MSS 2, 3, and from the Landsat 4, from the Landsat 4. Yes, we both launched the MSS and the TM. And then now Landsat 5 launched for 1984 to 2011. Yeah, several times. Yeah, this is also can be used on the orbit now on this one, and no, this is no, did not, it's failing. So no data, And the Landsat 7, Landsat 7 can be now used, also be used, but this one, Landsat 7 have some problem, because it's let me see. It's launched 1999 in the it's okay, but in 2003 on the May 30 first, this day, after this day, the data gap problem have the data because of the scan line character failure. So after that day, yes, 2003 May, the data have some gap problem. Yeah, gap problem. So we the America Landsat launched the Landsat 8 on 2013. Yeah, 13. Yeah, this one is very good. It's very good. And the Landsat 9 will be launched, yeah, only end of 2020. But now, today, not launched. I have not any, information about it. Maybe delayed. When will it be launched? I don't know. So, yeah, so if you want to the long term change, Landsat series may be the best data source you will choose. Because the same platform, the same source, data source, you can use in the yes, across long time, 40, 50 years. Okay, so it's very good for the change detection monitor and monitor. It's very good. Okay, this is Dataset series, and this is some parameter for the system or two systems that MSS and TM. So here is the spectral resolution, you see, and the sensitivity, spectral resolution. This is spectral resolution is yes, 8 meter, 8 meter, and in its for TM is 30 meter, 30 meter, and its quantization levels is 6 bit, 6 bit, but for TM is 8 bit. So the color, yes, the values is more. Yeah, I mean, you see here is on less than 100, only 64 values, but for TM, yeah, 8 bit we have the 256 values, so can more sensitive to the difference of different targets. Yeah, okay. So it's good. It's better. TM better than MSS by the comparative. Yeah. Okay. So special here is the special resolution, and this is for the we call the and radiometric resolution. Okay, it's different. This is we compare the Landsat TM and the MSS. This is but this is data. You gap that gap problem ETM plus. Yeah, and 8 yeah, it's very good. Now still can be used. Yeah, and we can download it freely. So it is most popularly used for for research, and for other application. Okay, it has 2 sensors. One is the OLI, it's operational and imagery, and the TIRS is thermal infrared sensors. TIRS. So the spatial resolution is different. These 2 sensors. For the OLI, you see here is 30 meter band chromatic. You see, maybe someone asked, what is the band chromatic? You see, this is the band 1, 2, 3, 4, 5, 6, 7, 8. Yeah, you see this is the wavelength. Yeah, but you see the panchromatic, it's the wavelength. It's from 0.5 to 0.68. 68, maybe from here to here, from these 2 bands. So this is the panchromatic. The wavelength, the range of wavelength is wider than any bands, but its spatial resolution is higher, only 15. Yeah. For the TIRS, thermal infrared sensors, 2 band, its resolution is 100 meter. So these 2 bands, yeah, you see, this may be used to you can see what land use, land cover. Yes, to classification for different land use in the land cover. And here the thermal infrared band can be used to detect the temperature of the atmosphere or our environment in our environment. So you can be used as a global warming, or the urban greenhouse effect, such as that. So it's very popular now thermal with the global warming. So it is be used more popular thermal infrared bands. And we introduced the Landsat series, and the next is the AVHR. AVHRR. It's also for land cover the characterization in the mapping of daytime and nighttime clouds. Yes, and it can be collected 2 times instead, but its spatial resolution is lower, 1.1 kilometer, and the Landsat side TM 30 meters. This is 1.1 kilometer, so more lower. But it can cover the global, so orbit Earth 41 times daily. So because the orbit is very high to our Earth, okay, so it's very can be used to detect the global, our Earth. Yes, I used this image. It's a very big area. Use this data. Okay. And this is for the AVHI. It's band, 5 bands, and they, including visible band, red band, nearly covered, and near infrared band, and the remaining 3 bands is the thermal band. So it's used for clouds, snow, ice, sea surface temperature. Okay, yeah. Also vegetation, because these two can be used for vegetation, visible in the near infrared 2 bands. But this may be more useful to the temperature. Yeah, temperature. And this is the AVHI, some sample images from the AVHI. You see band 1, band 2. Yeah, here. This 2 band is visible and near infrared. This is the black here. Black one is the water, and this is maybe the wetland, water wetland, and this is maybe some land on the water, and you see here maybe some wetland vegetation. So here in the red band, here vegetation, the digital number is lower, so the color is black. But for the near infrared band, the vegetation, the digital number is higher, so vegetation may be the white or shallow gray or the gray. And this is maybe the crowd, you see, high digital number. This is the crowd. And the others is other 3 is thermal bands. Now, and this is for the typical spectral reflectance curves of vegetation, dry soil, and water. You see, the water is a very lower reflectance because you see the water, each image, the water is always lower, lower digital number because its reflectance is very lower. So digital number is lower. So the color is black, black. And you see here, this is for the vegetation. Yeah, in the visible band, it's lower. Particularly in the red band, this is the red band here is lower. But for the near infrared, you see here vegetation in the near infrared band, it's higher. So here the color is whiter than this one, vegetation. Okay, and this curve is for the dry bare soil. Dry bare soil, the reflectance is linearly increased linearly until here, then maybe up to a balance, to a yeah to a balance. But here linearly increase decrease that a dry bare soil you see is maybe the dry bare soil, or maybe the cloud. I'm not sure. Maybe the cloud, maybe the dry soil, because this is the water or the sea. Yes, and it's around maybe perhaps bare soil, sand, such as that. So this is the ABHS. Third, we introduce spot. Spot is from the above two is from America, and this is from the France. France. Yes, it's first launched in 1986. I also have spot 1, 2, 3, 4, 5 until 5. No, not any 6. Okay. So it's the quality of this imagery is very high, very good. Okay, and you see this is the sports 1, 2, 3, 4, 4, and 5 is yes, and still be used now. Okay, and because this is from the textbook. Okay, so some older did not updated. Yes, sport 5. 2008 launched. This is a sport satellite system components. You see, this is a HRV. Yeah, and this is for the head here. Okay, sensor system different. And here is the sport. Here is the can see the viewing can be the vertical viewing, also can be oblique viewing, oblique, vertical and oblique viewing. If you see from the oblique viewing, you can see the height of the building or the trees, So sometimes if we use Google Earth, in China, Google Earth is forbidden, but some archived, some cracked software or the applications can we can get some from different ways we can see these Google Earth images. Sometimes we can see in the urban, some buildings have height. So why it have height? Because it's used the sport imagery. Because sport imagery can both view from the vertical and the oblique. And this method can get the height, of the building or the trees, such as that. And and the sport, it's swath readers and another 6 kilometers to and it's one Swiss width is 60 kilometers, 60, and two census covers 117 kilometers, not 120, because some here the boundary is covered, partially covered, so total width only here is two so this is a sport. The quality is very good of sport. Okay, but this is not free. You should pay. For this image. But for Landsat, but now, do you know the sandy shore? Sandy shore. San, this data is from Germany. It's free. Sandy shore. Sentinel, Sentinel, Sentinel two, Sentinel. Yeah.
Yeah, Sentinel. Yeah, yes.
Sentinel. So I said, I pronounce it Sentinel. Sentinel two is free and it's very good. And only the visible band, the special only 10 meter higher than Landsat. Okay, it's very good. Also, it has a radar band. Can be used in the rainy or the very cloudy conditions. And 10 meter special resolution for the visible band, near infrared band. Okay, so sport is not free. You should pay. So now very popular is Landsat and Sentinel. Because radar is maybe more difficult than optical image to process. Only see from radar you see the white and the black color is not very friendly, but for the much spectral side, the optical imaging, it's the color you see it use the eyes and more friendly, more like the optical imagery. Okay. So it depends. Um, but the radar have its merit also, and the optical imagery also have its shortcomings. Maybe both have be fused together, combined together is better sport. And next the fourth we introduce the EOS Terra and EOS Aqua. And why the different? Because the Terra is Landsat in the morning, and to is the AM satellite, and Aqua is the PM afternoon, yes, satellite. So can maybe, but for here China, we use this Terra AM, most sometimes the PM. I'm not sure because more popular PM or AM. I'm not sure because seldom I use this models. I used the Landsat Sentinel, yes. But models maybe I'm not sure. Okay. So two times daily, 2 times daily. So here we introduce the Terra-AM satellite. This uh, to Terra instruments have uh, sensor have 1, 2, 3, 4, 5 sensor monitor, five sensors, five sensors. First is Aster. Aster is um, because it is mm, same. I think the Aster is the same as the Landsat TM, Landsat TM, but not very popular because it launched um, 2000, 2000. But Landsat is um, one 1970s or 1980s. So, yeah, long history. So, its special resolution and is the same as the Landsat TM. And the second census is Ceres. It uses across and as a radiant image system. And this is multi-angle imaging spectral radiometer, multi-angle spectral radiometer. So it's very good, but the spectral resolution is very low. If you to your study area is global, or the all country very large area, you can use this. But because you can get it, the height of the trees or building height, and also its spectral radiometer is more bands, lot of bands. So, but the shortcut is the special resolution lower. Okay, and the fourth is Modis. Modis is very popular, and we will more popular. Okay, so Modis, and the last is MO Morpit. Morpit. I never used that. This one. Okay, the fifth. Okay, this is a Modis. Okay, this is the first global coverage. Yeah, this one. And you see, moderate, because the special resolution for moderates is different. Say some bands have 250 meter, some is 500, and others have more than 1 kilometer. 1 kilometer. So it is also suitable for whole country or global vegetation or air or water pollution, something like that. Use this data because its spectral radiometer have 38 bands, 38 bands, and it's free, also free, also free. So very good. If your study area is larger, you can use the models. But the models you only can use the from 2000 because it launched 1999. Okay, so you get the from 2000, and before that, no data. Okay. And this is multi-angle image. You see different angles, so you attract the height, yes, of uh, the building, trees, the height, because it's multi-angle. Yeah. And this is gears. Gears is okay. Gears is we used for the. You see, this is how the height. Yes, the height um, from our Earth, the orbit height is um, 35 or 35,000 and 8 kilometers. So very high. Above the high enough to allow set as a full view of Earth. So it was used for weather forecasting. In every 50 minutes, we can get get an image very frequent, very quickly. Okay, you see this is east visible infrared, and this is also the east water vapor. This is for the forecast. You see here is the typhoon, and maybe the um, wind, the rain, all come with that. Okay, you see, and the special resolution is very because it's very high. So the special resolution is very low. Low. This is the visible band, and the others is um, moderate infrared. Yes, moderate infrared. And we introduced the moderate or the coarse spatial. So and then we will introduce some high spatial resolution. And they use the linear array detector, such as quick word econos word view. Word view. You see here, Econos originally the company is the GLI, but GLI was yeah be bought by the digital global, so no GLI. So also only have the digital global. So Econos also from the digital global. Okay. And you see, this is a quick word 2002, and the special resolution is 26 meter in pan sharpen the image, so it's very clearly. You see the building and the green roof. You can see red roof, trees, shadows. Yeah, very clearly you can see. Okay. And this is the choose on the Econos. Originally the Econos is 4 meter for the multispectral, and the panchromatic is 1 meter. So if we fuse the panchromatic and multiple bands, then we can get this image pan sharpened multispectral with the special resolution 1 meter and 4 bands. 4 bands. So this is very good. And we will to exercise this how to do the pan sharpen, do the pan sharpen. Maybe at exercise 4, we will do that. We will exercise that in the level 4. In the level how to do the pan sharpen. Both high spatial and 4 bands. And then this is a world view. This is also their 2 meter resolution. This is Colosseum, Rome, Italy, Colosseum. And this, there. What is you see? This building is white. Oh, red one, red one. Infrared, infrared color, infrared color. So this color is green, because infrared color, force infrared color.
I think lashes reflect to the like green or trees.
Yeah, I maybe this roof, the color of roof actually natural is the green. Yeah, because it's the force infrared color.
Yes,
So you see, yeah, in force color, not natural. Um, I never go to the room. So this time I choose this housing to room. I will to find to um, uh, see, yeah, whether it's the roof of the green is green. Green. And this is a normal color. Uh, let's